physicist, I think, hope. And I've landed in Brazil. I don't speak very good Portuguese, despite the fact that...
That's not a joke.
It's really, yeah. I know I'm come from Portugal originally, but let's speak English, okay? Because Rogério now has been such a kind host to... is forcing me to speak Portuguese, and now I speak very good Portuguese. My husband will be... so I'm a cosmologist by trade. I came for a conference in time, and Rogério has been such a lovely host in showing me around in São Paulo and this incredible infrastructure for cosmology that you have in Brazil and in São Paulo. It's very humbling to speak here because Brazilians are incredibly smart. I know you're going to say it's not true, but it is actually true, as you will be able to probably...
From Minas Gerais, right?
From Mineiro é... Are you Mineiro? Oh, what's your name? All right. So, I asked Rogério not to have to introduce me because I actually have... I'm going to speak today on dark energy. So this experiment DESI has been claiming to have excluded ЛCDM. Raise your hand if you're not a cosmologist. What kind of not cosmologist is this? Are you you're a physicist?
I know about cosmology, but I'm not a cosmologist.
But so the physicists?
Yeah, no, he's a real cosmologist. But we have students also.
Yeah. I mean, I'm not talking like to mathematicians or chemists. Okay. Yeah. So yes. Yeah, and interrupt me. I'm I spent a lot of time at Perimeter Institute and in Berkeley lab, where I was a postdoc, and we have a tradition to interrupt people all the time, which is not true in Portugal and in Europe, and I've noticed in Brazil people don't interrupt a lot as well.
You're interrupting all the time.
Okay, fantastic. So I have this slide here just to say more or less where am I coming from. I'd like to give this slide. This is the work that I do, or this was through at 2020. It's a bit old. But I like to give this slide because it shows a broad range of work that I have done. And for students is interesting because when I was a student doing a PhD, I thought that we only have to do one thing. Is any of your students here? Because I'm talking to them, so they don't, I'm going to say something. Maybe the supervisor is not going to like what I will say. But I do believe that we don't have to focus so much, specialize in one area in cosmology, or even outside. But in my PhD, I was worried that I was doing a broad variety of topics in cosmology, and I was not going to get a postdoc. And then afterwards, I got a postdoc in this. It was the Berkeley lab, which had the only Nobel Prize in cosmology at the time, George Smoot. This was in 2009, 2008 when I arrived there. And I arrived at the Berkeley lab and I said, "Oh, George, I'm so sorry. I know that I work on many different things, but I promise that now I'm going to focus and I will just work on one thing." And he said this amazing, surprising story. He said, "Oh, what? Don't specialize. Why do you think we hired you?" And I was like, "Oh, so it's a good thing to work in more than one topic," because at the time I thought that you'd have to specialize. So I've worked here on the part of data analysis. Later on, it will become clear why I am doing this. SDSS, which is the precursor for DESI, was the Sloan Digital Sky Survey. It was called BOSS later on. SDSS was BOSS. Oh, this is DESI. It was called Big BOSS. I did some Planck. Yeah, it's funny, right? It was, I did Planck and I did some salt supernova filters. This was back in 2009, and now this has become more or less the Hubble tension, as you will have heard it. Then, if your supervisor has told you, we've all had a big trauma in 2014 2014, because we thought that, I'm still recovering from that trauma, we thought that primordial waves had been discovered. It's like Christmas coming. But then...
Has he recovered?
I never recovered, I don't think so.
That interview probably not.
And then I've done Eric, work with Eric, Linda, who's in DESI, who's going to become possible for DESI. Then this is inflation phenomenology. So the curvaton in particular here, Burns, Cortes, and Liddell is an article that is out today. And then even more wild, I went to fundamental physics, which is a talk that I was giving earlier this week, this conference called Time in Cosmology. And my work with Lee Smolin actually won the first ever Buchalter Cosmology Prize. Does anybody have heard of the Buchalter? Oh, wow. Yeah. Okay, cool. Look. It's a very important, it's the only cosmology prize that we have, I think. And now it's a big deal, but maybe it's for more, more fundamental theories. So this is irreversible general relativity and quantum mechanics, retrocausality. So why have I not recovered from the bicep trauma? Because particularly after the Planck satellite, whose results came out in 2013, we all, cosmologists, we have been hoping to have anything to grasp on rather than having to tackle this ΛCDM puzzle from the theory side, which is almost impossible. And so one of the reasons DESI was a little bit, like a little trauma, not very much, but we were, Andrew and I, we kind of were told that there was going to be a new experiment result 48 hours before, and that there was going to be a great detection of evolving dark energy. And I couldn't sleep for 48 hours. I was like, oh my gosh, this is coming. And then the articles were out, and from DESI, this was in April 4th of 2024. This is the sign of trauma is April 4th. And then because we were hoping that the detection of exclusion of lambda was very strong, then it was a little bit of a disappointment because it became very clear in the abstract that the collaboration wasn't yet certain of the results, which is, as a first year result, is very, 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 very good to do. So, and you put these things, all right. I thought this was, yeah, so it is very interesting that they use this word tantalizing for the first article, and I'm quite sure that it's a word that's been agreed, and the researchers have been very, very cautious about it with good reason. Anyway, so I was in this collaboration, Big Boss, and I had the privilege. At the time, it was very boring because I was more of a theorist, and I thought, like, well, I have to do this now, and so. But this researcher Patrick MacDonald, who is an absolute authority on data analysis and building infrastructure for data pipelines, helped me out, and I produced the forecast for DESI on my computer according to several configurations for the experiment. And so even though this is being recorded, I think it's okay if I say more or less, how do I look at DESI results? There's a few people that I like to see always, not that the others are not building the experiment from scratch, but like I like to see Pat's name, Bob Kahn, who's a very, I respect him a lot as a very responsible and authoritative figure within the collaboration, particularly Berkeley Lab. I like to see Kyle Dawson, don't know where he's, over here, and obviously Martin White, who is at Berkeley, is, despite not being is also at Berkeley Lab, but is a very respected, very authoritative theorist. So if there is a result that is going to give a Nobel Prize, you want to know that these are some key figures. They're going to be supporting these in the first few authors, I would say, when we look at the list of authors. So that's what I was expecting to see when on April 4th. Now, the director of DESI, who was heard? You've heard? Michael Levy. So he's incredibly strong from the particle physics community, and it is a little, it's a different tradition than we have in cosmology. The collaborations in particle physics are very sound, very robust. They like their data to be very well analyzed, and also they're more ambitious than we are, I believe. For example, in the DES survey, we're more relaxed in that kind of thing. So, but otherwise, you see over here. This was in 2011. You see this is Saul Perlmutter, Will Percival, John Peacock, all wonderful people that we respect a lot. Nathalie, at this point, she's now director of a very prominent figure in DESI. She's, I believe, director of the Department of Physics at Berkeley Lab, and she gave a talk on the day of the first result of DR1 at the Royal Society. So she's also very, I like her a lot for being very responsible with the data analysis. This was the early abstract. I think it's interesting to say just one thing. So DESI has the BAO, Baryon Acoustic Oscillations. Is that okay to say? Or do you think? It's like something acoustic exists in particular one scale, which is the acoustic scale in the power spectrum. And it has broadband. And at that time, it was uncertain how much money we would have for the mirror. And so the broadband power spectrum, which now we call, I think in the literature, is called full shape, is more expensive because if you want to go to small k, not small, small scales, meaning higher inverse wave number k, the lens is going to be thicker and more expensive. But particularly, I remember here at one point we wanted to have a smaller scale structure because that will give us constraints on the neutrinos and on early universe inflation. And I remember asking how much more expensive was the mirror going to be for the early universe, and I think it was about $3 million to have a better lens. So this is what I'm going to say here. Yeah, and so this is the figure of merit of the dark energy. This was the dark energy task force, and it was different. It was very interesting for me to be at Berkeley Lab at this point because we were all discussing about the numbers here. And I think it's a little different to be at a national laboratory as opposed to be at a university because it was very good to see the dynamics over there. So the point here is that if you take the galaxies, all kinds of galaxies, I don't know if here we have, so we have the BAOs, BAO scale, several galaxies. Then we put the Lyman alpha. Is that Lyman alpha okay? And then, of course, if you have a smaller scale structure, then it's going to be a bigger figure of merit. But the analysis of the Lyman alpha forest in smaller scale needs to be strong theoretically. This is why it's good to have experts like Martin White and Pat McDonald to know that we can trust the constraints coming from Lyman alpha. I think you had a question? No, maybe not.
Just to clarify with my students, because we didn't see this in the course, but so Big Boss was not built, not as Big Boss. So what they did was to have figures of merit. So this is using some statistical tools called Fisher matrix, which we did not talk in the course, unfortunately.
Yeah.
But then the larger figure of merit is like the inverse of the error.
Yeah.
Matthias knows all of this, but so just to make sure that people understand. So the larger the figure of merit, the smaller error we have. So this is an estimation of the error in the experiment. And and you want larger numbers. So this was a forecast.
Yeah. Yeah. So eventually the ellipses come something like this, and the inverse of this area shows you how strong the constraints are. I actually the W0WA is called the CPL parameterization. Did you cover that?
Yeah, I think we talked about
CPL, okay, yeah. So that's a figure of merit, right? So, and then this was for the neutrinos. So this was made by my computer, and it was code built by Pat McDonald. Again, why I look for particular names when I go to look. So this was the constraints. This is alpha, the running of the spectral index, inflation, and these were the constraints for NS. Let's go forward. So we'll start on I wanted to give that preview of how the experiment was built, DESI, what is today DESI, so that you can have an idea where is the situation coming from, where we are today. So this is the Planck, how call that? Not a trauma. I mean, it's like a little disappointment that we didn't find more parameters, the universe to be more complicated. When the Planck results came out in 2013, it's almost as if the universe is the simplest it can be. It wouldn't give us any extra parameters, so we can try to explain why do we have these funny values for the fundamental parameters here, the baryon density, cold dark matter. What is this now? I don't know what that is. The optical depth. What is this?
So theta c is the angle.
Oh, okay. And then this is optical depth, and the amplitude, and this is the scalar. The scalar spectral index of the scalar perturbations in the early universe. It's actually a big deal because this is how we explain or hope to explain how the universe started and why we see a lot of all these structures we see today. So even though it looks very complicated, this is spectrum of the CMB, etc., but it's actually from the underpinning philosophical point of view, it's a big deal if you hope to be a sound cosmologist one day. So we were a bit disappointed. And then, so let me just see, but then. So what is interesting here? DESI is a DOE-led mission. And despite having, I think there's maybe 800 members, this is the Department of Energy. So it's a federal government, US government experiment led by DOE, meaning the first main funding comes from DOE. And it's very important, and why I've been very careful while I've discussed the results of DESI in the press. It's in the following sense. We want to be careful with the results, and everything that I might say that, okay, we need to be more careful with the data analysis, that's okay. But yet, I have a deep respect for the researchers building this data pipeline, and knowing that we do need to have the funding from the Department of Energy for the mission to continue and to have what is now called the Stage 5 DESI follow-up, the Stage 5 spectroscopic experiment. So while we might be a little bit critical of the theoretical analysis, we want to emphasize that these are the best people in the planet that you could hope for, very, very responsible with their data pipelines. The first data result came saying that we have maybe some sources of evolving dark energy. Do you think, do you guys know that, so the first result of DESI that came out last year was that the dark energy is not constant. This means that if it was a scalar field, it would be a canonical scalar field, which means that the energy is conserved essentially. It will be easier, and there's a very rich variety of theories to explain how the dark energy evolves. The problem occurred because it came out as being this thing called phantom. Does anybody not raise your hand if you've not yet heard of phantom dark energy? You've heard, right? Phantom crossing. Oh, it means it's this funny. Of course, this is almost like a philosophical. It's so funny. So it's as the universe expanding, phantom energy density means that not only does the energy stays constant, even if I expand this room, but more energy pops out of nowhere. So it's not physical, because otherwise we would need, like, for the conservation equation, we would need a source, something that, you know, pulling like the petrol inside the room to explain where the energy is coming from. So that's why we're a bit uncomfortable with being phantom, is because after all, this still has to be like a coordinated effort of physics. And when we, you know, as a cosmology community go in to deliver the result at the door of, I don't know, Ed Witten or the string theory people, they're going to say, what on earth have you guys been doing? What am I supposed to do with this phantom thing that you've discovered? So the big vision that we want to have as cosmologists is, right, so data is incredibly difficult to analyze, but remember, you know, our undergrad in physics, and ultimately our community is going to be responsible for the funding that is going to happen in the next few decades. So what happened here was that they did the analysis, so that the pipeline was incredibly done. Like I said, all of those collaborators that I mentioned before built the pipeline for the data analysis very well. But then when we want to infer constraints from the data, we have to give a prior, this thing called parameter. I don't know if you frequentist or Bayesian. I don't want to start in that fight here. Should I talk Bayes? Bayes, okay, Bayesian. So thank you. So we have to put a prior on the data analysis, and the prior here was used between -3 and +1. So between -3 and -1, that's all phantom.
For W0.
For W naught, yeah.
And WA was -3 to 2.
Yeah, exactly. So yeah, so this is the exactly, and then this is the W naught WA here, and the cosmological constant is W naught equals -1. And it's called a phantom regime. And what is the problem here? Let me see what Andy put next. Oh, right. So DESI had, they have galaxies and quasars, but ultimately you're going to need a supernova, and then you have to choose a supernova data set. And there are several data sets of the supernova, but when combined with Pantheon Plus, it was still, the results turned out to be consistent with W of -1. So if the results are becoming dependent on which supernova data set you choose, then we start to be uncomfortable. And this was, the team were incredibly responsible. They were in the press releases and in the data, the articles, they were very careful. Then we started to see a lot of attention from the press. Which is, I guess, okay. So this is their result, the W naught WA parameterization, which is this plane that I've shown you here. So I should have drawn the ellipse in this way. And so between here and here, this is all phantom. And yeah, this side. So if the data end up over here, if we choose this as a prior, we're not going to have a good physical foundation for the models we observed. And let me see. And on the right-hand side, you have there in orange, blue, and green, different supernovas combinations. So the BAO data from DESI plus the Planck satellite, and this is supernovas. And so these guys in the supernovas have been giving different results historically, so we're a bit nervous about what to make of that. And Andrew and I wrote this notice that they have, if you're making a measurement on data, you have this scale in which your experiment is going to give you the optimal, more constrained volume in data set, which is called the pivot scale. And they used, let me see which one. So the equation states our dark energy measurements is going to be best constrained. And we got the samples of supernova have pivot scales from Pantheon and DESI, not the DES, year 5, and Union is another one. And then let me just see what we found here. So we found these are the models that are phantom, and some the ones that are always phantom, the ones that are never phantom. These ones, for example, are almost never they're never phantom. So this part here is good. Phantom today is over there, and then we found this coincidence of these lines with the pivot, which means all of these supernova data are giving the best pivot at the exact time where the dark energy fluid is changing from phantom over here below -1, this is the dark energy, onto non-phantom, and this is looking back in time. So this is now, we look over here, and the pivot scale of the experiments are all more or less around the time that the fluid is crossing from being phantom, this like thing where the energy pops out of nowhere, to being canonical, normal physics. And so it's kind of, you know, as cosmologists, you kind of feel uneasy about the data. You'd prefer that you don't have coincidence popping out. So this was the first thing that we mentioned. It was very easy to see. We call this the phantom crossing coincidence. I believe that you guys, from the more fundamental part, it's very difficult to make the fluids cross, right? If you have like a tachyon fluid, you don't want it to cross, to go from phantom to quintessence. I believe that's the case. So this is more weird. So our article got, I think it has a lot of maybe 100 citations in 1 year. I think it was because we knew, I was in Big Boss, so I knew the people, and I felt comfortable about what was going on. So the funny thing about the community worldwide was nobody was very happy to receive the results and say, oh my gosh, my phantom model that I had is correct, because we don't have a model that is for dark energy that is phantom. Somebody knows something? You you want to say something maybe? No?
No, we can have interacting dark energy, dark matter models that mimic phantom.
Oh yeah?
So,
Yeah, so exactly. I think it's also the Paul Steinhardt. Yeah. Did you? And you also have your model. So later on, the ones that are always phantom, but might have been quintessence in the past, you can have that as well. But to be always phantom is the one that you said, interacting.
Interacting can have this, so it's not a pure canonically normalized kind of without interactions. It's canonically normalized, so it's kinetic term is possible.
Oh, okay.
But has some interactions. Of course, you can have some models with non-canonical kinetic terms.
Yeah, and those are more
It's
difficult.
called K-essence.
The K-essence, yeah, exactly.
This can also explain this type of things.
Oh, okay. So that's good. And yeah, so from my personal perspective, from the theoretical point of view, is if in 10 years' time we see the data is definitely pointing towards a phantom, final, and we have to look into that. The discomfort came from this, having such a large prior, and I don't know if I disagree with the other author, Andrew, somewhat. I think a good prior is good, a large prior is good. Some weight maybe can be given to the theoretical motivation for our priors. Not too much, but obviously if the data is strong, it doesn't matter what prior you have. So that's the situation we want to be. DESI did a few more results. Emergent dark energy. And then over here, it looks like, so this is a team article. Definitely the result seems to become weaker over here towards the blue side as more data sets are added to DESI DAO. I'm going to skip these, you can say this later. So right now what we have, the papers that came out in mid-March is this one in the right-hand side panel. Do notice it looks like the data has been shrunk, but actually the axes are different. And if you don't have the supernova, so this is -1 to plus 0.1, and this is, so all the data is more or less, so over here, -4, gosh. This axis is much bigger, so it looks like it is shrunk, because this one is over here. And with that, so this is the three combinations, the three colors, blue, orange, and green for the supernova, different data sets, Pantheon Plus, Union 3, and there's year 5, and then just with the CMB. Planck and DESI is over here, so it's a big difference. We would like that DESI came out, and this is DESI in 2025, and then we put the supernova goes all the way over there, but then the supernova gives different results, and we kind of, something needs to happen. We need to look into this more, this carefully. Different axis range. So our results in 2024 are maintained. What we noticed, and this is what I think here now, is in the March results of this year, they gave 3 different sigmas for the exclusion of lambda. 2.8 sigma, 3.8 and 4.2 for the supernova compilations. So these 3 things here give exclusion. This is lambda? Yes. This is lambda. We are away from lambda in this axis. Just the fact that this is a diagonal, as a data analyst, you kind of feel a little, can we look into it further a little bit more? But also, we have several sigmas, and what I'm going to say, none of the above is the correct. As I say, Andrew wrote the slides, but yes. So what we did was, when you have different data sets that are giving different indications, we have to go use our opinion as physicists and look into the data and see, okay, how can we treat this statistically? Let me just see. So Andrew he derived this error function, which is when you have data points that the data sets are not entirely independent. Some of them have mixed, they use the same supernova, some have different supernova. So from the statistical point of view, it's very important we know what we're doing. And later on, I'm going to talk a little bit about AI. And this is where we get all of our training to understand artificial intelligence models, because we have to be very, very good at analyzing data sets and inferring what the data set is saying in cosmology. So this is, I'm going to go a little later. So if you have all of these sigmas, then this analysis using that error function says that we came up with an overall exclusion of 3.1 sigma. And hang on. 3.1 sigma. And the funny thing was that the 3.1 sigma exclusion of lambda CDM is the same exclusion is if you don't use any supernova, just Planck and DESI.
But by eye, looking at DESI and CMB, it doesn't look like 3 sigma.
Yeah, that's
Because it's a huge thing, so
yeah.
sigma is much bigger, no? So for me, it's less than
I think because
half
they
a sigma.
so the 3.1 sigma is our calculation using the statistically correct formula. So that's why.
But combining it in 3 supernovas, right?
Yes, yeah. In the way, so you look at which ones are in common,
Right.
which parts of the data are independent. So you don't put in the same stock or counting twice.
No, I understand that. What I don't understand is the 3.1 sigma for DESI plus CMB only, because it looks much bigger there.
Yeah. So this is by the DESI team, and we use that.
You have 2 contours, 1 sigma and 2 sigma.
Yeah. but
Hang on.
the
Let me.
difference of 3
Yeah.
sigma is between that and 0.
Just 1 second. Let me see where I've.
So it's like 1 sigma, no?
Yeah. Let me see where is this formula.
1 sigma.
This 3 sigma contour is not wrong, but it's just a little bit bigger than 2 sigma contour. So
Just 1 second.
You're saying that
that you see that
Yeah.
top over there is 2 sigma contour.
that's right. That's
So if you go a little bit further, is the 3 sigma contour.
okay. Yeah, you're right. You're right.
Hang on.
Okay.
So, Jose, this formula here is what we used for the combining the supernovas in the absence, in the presence of knowledge that some of the results are the same, some of the data points are the same, and without using more prior.
I have to check this 1 sigma to sigma. Right. So the two dashed lines is 1 sigma to sigma?
I think that is 1 sigma to sigma. I want to move forward, but we can even call Andrew stronger constraints. Yeah, so here is the different parts. Pantheon Plus, they have a salt, a supernova light curve fitter. Union 3 by Dave Rubin, who I adore. They use a new light curve fitter, and this year 5 you have an expert, Rogerio, that is going to understand. But so there is historical samples in the supernova that are quite old. The supernovas don't pop up all the time, particularly the ones that are in very low redshift. I believe that those are quite old, meaning maybe not all the systematics was attained or was accounted for when those supernovas exploded, maybe 20 years ago. Maybe some of them could be as old as 20 years. Historical samples. So these are the difference. I can go. I want to move on, but so we need to look at the supernova a little bit more data. Let me just see here. So if we use different supernova, they are not consistent, or they're not completely counted twice, or not being interconsistency, you're going to get problems. And so we shows that making the best combination of the data by the supernovas, you get an uncertainty of 3.1 sigma, not so much as the ones that you're getting from different supernovas. And that means that maybe the supernova are not, if we take into account the uncertainty when we are measuring using different data sets, maybe they're not doing something or a lot. And this kind of makes us feel good that we combined the uncertainty in 3 data sets correctly. Let me see if I...
About the priors. Did people try to change the priors? See what happens?
No, they did not show that analysis, I believe, to my knowledge. As you know, we hope that as more data is added, we're going to get prior independent. So we don't want to criticize a lot about the priors because it's the first year of data, and so
Now it's the second year.
now is the now is the second year of data. But you know, like it's hard work. They're doing comes from the supernova, which is a sock drawer essentially.
The prior and pipeline shouldn't be difficult.
Yeah, exactly.
Just run again the pipeline.
Yeah. So I can have two answers to that. If I'm talking to somebody in the press, I say, no, don't worry, this team are doing the fantastic work, and in a few years, the typical procedure in our community is to get prior independent data. That's what I would say to a reporter. And we need, DESI needs to keep getting more funding, because we do need, you know how the funding situation is evolving worldwide. We do need more to continue to get more funding for the mission. If internally, then between friends and colleagues, we might have disagreements, but that is within from professional to another professional, right? So that's what I have to say about the prior.
Just ask, so the coincidence there that you said before, that when you go from phantom to non-phantom is the observation for supernovae or also
for supernovas? Yeah, those three data sets and supernovas is kind of, if you twist, it's almost like as if you were twisting the data set in a parameter space and you're looking at. So if you look from here, imagine I have like a banana shape. I look from here, it looks, oh, this is really uncertain. But then you twist it around a little bit, you look from here, you see, oh, if I marginalize around the other parameters in this direction, maybe I have more information there. But you know, it has to be done consistently, because you can't forget that actually you're looking at this like a circle, but you know, there's hidden uncertainty. If I look to you through these and then have a telescope that is this big, if I twist it around, you see that the data are more separated in parameter space. So the priors, the pivots were for the supernovas only. Let me just see what I wrote here. Right, because I wrote something here. So this is currently, Andrew and I want to try to understand what is going on in the supernova community, because this has been going on for years. I mean, WMAP, in 2009, WMAP 3 or 5 already excluded supernova because it was giving completely different results for the CMB. So they excluded it. And at that point, I like to bring communities together. So I said, okay, let's get everybody together, let's try and look what's going on. But the teams have such different methodologies that it's been difficult. So before I go on to the inflation, what I would like to understand by talking to the professionals in the community is their advice in the supernova that, guys, we get new supernova at very low redshift. In very low redshift means below Z of 0.1. I don't know. I think it's between 10 and 20, but I could be. Do you know? It's small. A small number of supernovas are anchoring the age of the universe and the data at locally where we are. So that's below redshift of 0.1. These are old and are creating a big problem, not only here in the DESI, but also in the Hubble tension. We don't know how old the universe is. If we don't figure out what's going on, it has implications for the global community in cosmology. Because if this result gets passed onto the phenomenology community, the theorists don't have an obligation of studying the data. They're going to take the data from the observers and say, okay, so I have to go into the theory. And if you tangle these two communities in terms of funding, it could be a couple of decades before it gets detangled. Imagine that we're walking around on the planet being cosmology observers, knowing that the theorists are spending grants millions of dollars possibly, studying something for in theory that we kind of know, oh, maybe we need the data to be a bit better. So that's this, I feel that today we are in this critical moment for cosmology of this phase I want to call it the lock-in phase, which is if the observers, if the theorists understand, oh, they don't understand what's going on, the observers. Let me write a grant for my European funding agency, American funding agency, Brazilian funding agency. I want to study why is a phantom dark energy, or why is the universe, the Hubble tension. Study it in theory. When this gets locked in the two communities, before the whole planet wakes up and understands, oh, but we've been wasting all of our money and all of our careers, because actually it turns out that this was an observational result. It could be quite wasting of the time of the entire cosmology community in the planet.
It's very depressing.
That's, yeah, precisely. And I think because we're done, because we are at that point in which we can still say, guys, don't take it away yet. Let us do our data a bit better. I start to see more and more respected theorists that say to me, oh my gosh, have you thought about the Hubble tension? This is fantastic. And I don't want to say, oh, no, yeah, it's really good. I don't want to say that it's not good, but I want to, guys, how can I express that we have a little uncertainty? Please, we're still playing with it. Don't take it away.
Well, to be fair, some theorist papers, they start the following way. So we have this data, there's tension, we know that this tension can be solved by systematic errors.
Yeah.
Here we're going to take the more exciting path.
Yeah, exactly. Yeah, exactly. So if it stays like that,
The other way around.
they start the other way around. Oh, yeah, try not to look around. So I like that. If we keep in mind that we don't know very much. But what I'm doing today, remember when I showed you the slide that had the data acquisition here at the string theory or loop quantum gravity over there? There's not a lot of us that can articulate between all of these. And so I'm coming to you talking about quantum gravity, and then I say DAO galaxies, and I kind of try to keep it all together. This is what we have to do, but it's incredibly difficult, right, to understand the data analysis. When I say that DESI do a fantastic job, it's because I know them personally, and they're incredibly thorough at looking at the data. So as a conclusion, just on the DESI part, let me see if I have. The conclusion is just that what I've seen the DESI team doing is they want to be very careful and build a catalog for us of sources. And so they want to convey all the uncertainty in the data that they can control before we come with the theories. And that is a very good project, I believe, because then the theorists can come, and then we have to specify our models before we analyze the data. So that's what they're doing. Right, so this is a new paper that came out this morning. Let me just see. Right, so ACT, we were so, I had to do the curvaton ACTs again. I still find it very funny, these acronyms with ACT. So even though there's a lot of papers with ACT, the ACT again. Final ACT. Oh, come on, we have to have.
So we have to. Cosmology test. So people make fun of this acronym.
Because like we're little losers that don't have a life. So I like it. I know that we should get something more exciting, but anyway. So here is the what we all thought. I'm like a relatively young cosmologist compared to my husband. Sorry, it's not gonna go down well. So when I was young, like as a PhD student, this wasn't excluded. This is a Harrison-Zeldovich spectrum of inflation, not of inflation, of the CMB. And when the contours of the data, this is the spectral index of the scalar perturbations, and this is the ratio of tensor perturbations to scalar perturbations in the metric. So the models of inflation have always, well, there would be models over here, but this prediction that is not exactly 1, ns minus 1 equals 1, is very confirming. It's kind of, it was when people said inflation, you know, you wouldn't be able to get it. Now, it's been over on this side for a few years. I think Planck was over here. And now ACT, this result that came coincidentally around the same week, within 10 days maybe of the DESI result, they came out together. And they pushed all these contours here back to this side. So a lot of good models, I mean, good, like, well, can we be democratic here? A lot of good researchers that were studying these kind of potentials here. So this is, which one is the Starobinsky? This is the R-squared, the Starobinsky with all these power laws. And it turns out that it's more difficult to get those now. I think this one was the Starobinsky. And I think we just wrote a paper saying that the curvaton can actually, the curvaton model is an inflation model with two fields, and the F here, the ns minus 1, this guy over here, has a formula that has a number F, and this is the number of E-foldings. E-foldings is the amount of expansion that you have during the expansion of the early universe, during the acceleration, during inflation. And we noticed that if the Starobinsky people got out, we're back in because the curvaton had been excluded. So this was out today, out last night, middle of the night.
Any problems with isochronometry perturbations?
That's a good question for Chris.
So we just asked I read that there was a paper in March around-ish, right?
Yeah.
Where is that much different from?
Yeah, this is the
I mean,
this is the March paper.
It shifted a little bit, right? Or
No. I think this is all theirs. What is figure adapted? Yeah. So this is their paper. Does it not say there? No. This is their figure. Prior to ACT, you had Planck, which was.
No, it's already from Planck. I know, no, but
this is
exactly the March paper.
Planck is the purple one.
I see.
So the blue one. Yeah. Exactly. Gosh, now I'm looking. I don't know what is LD. I always forget. Lensing, the lensing B mode maybe. The result is more closer to this side, I believe. It's the purple one. So particularly this guy, which is the R-squared, was out. And now we wrote this saying, okay, if these results are good, the curvaton is in great shape, despite there being models left here. Again, if you pull out a little bit, what we seem to be seeing with the data is that if ACT don't have the, I don't know if DESI is combined here, but ACT used the measurement of omega matter. And the omega matter measurement seems to have had an influence on the NS to R. And in looking at some contours, I don't want to go into it, we can discuss later. Looking at some contours, it seems as if a lot of the shift is coming from when we put the DESI data. So we're kind of looking from the outside, we look at the DESI, on their own is one result. You put the supernova, you have a different thing. Look at the ACT on their own says something, and then you put DESI, you have another thing. We're kind of like, there's a circular argument. Like, where is the data coming from? And one thing that I really want to be very clear about, these are completely different data probes in cosmology. The BAO, baryon acoustic oscillations, using that with measuring the CMB from a completely different cosmological probe, all of these measurements rely very strongly on the number of assumptions that we put into. Are we fitting it with the ΛCDM? Are we fitting it with something that accounts for the systematics? So when we start putting everything together from fundamentally different cosmological probes, we have to be very responsible. And this is a difficult thing, and why it's so important that more and more cosmologists get formed in doing a little bit in data analysis. It's really boring, and I hated it also. But later on, I now see, I stand over here and I can look at it and recognize the community, and I can come and do a little connection in which I say, okay guys, so the theory, yeah, go work on that, but beware that we don't know this. And more in cosmology we need these results. The professionals that are able to talk to a lot of communities. We really need this not only in cosmology, but outside of cosmology. So in the last 5 minutes, I'm going to say, what can you do if you were a data analyst? You know a lot about data. I'm done. This is just artificial intelligence. So we hear a lot, like, I'm so lucky to have been funded my whole career by societal funds. I don't have a business, none of you have. And so having this academic community, and you guys are students, you will not be able, maybe you don't realize how important our value is. When we move outside of academia, everybody in this room, we're kind of losers in the sense of, like royal loser, like pure blood losers in the sense that we don't make a lot of money with our knowledge. And so what I've noticed is that when society needs us, we hear a lot of times that we have these jobs, the taxpayer cozy jobs. So they build our jobs, we're here, we play with cosmology, we don't give anything back to society. But actually, because we don't make money, and with our knowledge about data analysis, we can intervene when, for society to call upon us, when our expertise is needed. And so data analysis has been very, very important for me, because when the artificial intelligence models started coming out and people didn't understand really what was going on, it was very easy. If you did data analysis with Bayesian parameter estimation, you understand very well what the GPT or generative models are doing. And so I wrote this essay, which you can Google by, if you put imagining the digital future, and I was selected with a team of experts to explain what's going on at the planet, planet-wide. And so I'm not going to go over here, but Windsurf at Google has been doing also very good work on this, and so he was also duted there. And I am chair of this organization. You might not have heard of IEEE. They write the standards for safe technology. For example, the Wi-Fi. When we use Wi-Fi, the standards for what is a Wi-Fi signal were written by IEEE in standard, I think is 801 by David Law. So I'm chair of the safeguards for artificial intelligence. We were the first papers, the first working group that came out after President Biden issued his executive orders. Literally, I think we started about 12 hours after he issued executive orders on AI. And the powerful technology, the powerful approach is that an organization which is global, like IEEE, it's a volunteer pro bono organization, has a lot of influence when the European Union is giving advice on AI, the US government is giving other advice. And then we have a uniform safety approaches because we're not bound by a country. We can bring, say, what we see. So it's kind of like a United Nations, but for technology. And we issued a couple of papers here. All of these guys here are either based in DC, Christos is in the European Union. Ken Machuso is very funny. I think he wrote built a company that essentially became the iOS for the smartphone. Jane is cybersecurity in DC also, and George is from Athens. Some people from Poland. So we have like a really global analogy. Oh, gosh, I lost it here. The global approach, because we have a lot of members working at safety standards, and we do need people. If you want to help out to write the standards, it's basically, I can say that as the last thing, it's. You heard of the apagão that happened in Portugal with 3395. So what I built, that I advised for building these safety structures, the biggest challenge with AI is the building of safety networks for when big infrastructures fail. And in the case of the Portuguese energy blackout, there was a big problem because the dependency on automation was so large that the centralized government had no time to send, or not enough organization, they had time to send an SMS to all the population saying that there's no apocalypse is coming, there's no Martians invading the Russians, or what I heard. And this is just anomaly, and it's going to be sorted out in 1 day, 2 days, 72 hours. Because that didn't happen, in around 2 hours our supermarkets were empty. We had no idea what was going on. And so it was like a COVID in 2 hours. And I do want to say this, Portugal is a very safe country, and we were by the beach, it was a beautiful day, people pick up their surfboards and went surfing. That's what people were doing on that day. If it was a day in which the instability in society, a country in which instability in society is a bit more fragile, that could have ended up very different with people not knowing what's going on. And in societies that are a little less peaceful, it could have led to riots. And so, the challenge with AI is only our knowledge of the level of automation and knowing if something fails. We call this cascade failures. I think in Portuguese they're calling it, what's this thing? Castelo de Cartas? Is that what you say? Castelo de Cartas.
One card and everything falls.
Yeah. So this is the first thing that the internet founder Vint Cerf said about a year ago. He said, I'm worried about cascade failures. Imagine you get locked out of your smartphone for 2-factor identification, 3-factor identification, what's going to happen? Usually what Vint Cerf says has a way of becoming true. And I don't know how he knows so much, but it's really worrying. And so when we are exposed to the planet at the moment, if we can work out what the number of assumptions, again, Bayesian theory, the number of assumptions on which our lives depend on, and if something fails, what am I going to do if this fails, if that fails? That's essentially the artificial intelligence conundrum. The thing that Vint said on that essay that I think is very important, he is worried about how we're going to identify ourselves as humans. And now, again, it sounds a little bit, it's May 2025, so I'm human. But when he said a year and a half ago that we should be worrying about cascade failures, This sounds really solid to me, and now we're in this situation. So I had a way of learning through the hard way that what Witzer says needs to be listened to, and human identification, so you identify yourself as a human agent, might come to be difficult. But we're here together, so it does not. Thank you, guys.
Questions from Marina, or DESI, or intelligence, or the world, safety?
It was a long talk about many topics. If it's going to be online, you guys can email me later. And there's also my website is marinacortes.org with Cortes with an S. I did something, I had a Z, or my father had a Z, and then they changed it at birth for some reason to an S. Yes, oh yeah, no, came from Spain, Italy. Yeah, I think my family was Spanish originally. Okay, thank you guys.
More questions for Marina? Everything was clear? Yes.
Would you be able to make a separate claim on the statistical significance for early times, in particular phantom crossing? Or is it only tangled dark energy evolution?
The phantom crossing models have an early dark energy models, I think, have a very good chance of explaining the data if it becomes clear that it's robust to the prior. So again, as long as we know that the data is okay, and we have, like you guys have written, early dark energy models, that is I think it's very sound prediction. So what we need to do is to make sure, number one, that missions continue to have funding, so you have more data, and you become more robust in the predictions. And then also bear in mind what each data analysis means, so you can make an informed decision. That's really the best thing to do as a scientist, is to state your result along with all the statements that you've used for computing that result. Because then anybody can look at it and they look at the assumptions. If they don't agree with some assumptions, they can change the analysis.
Yeah, I noticed that they make an analysis by redshift meaning.
Yeah.
So that would, in a way, be a line of defense against people who want to validate the results based on the phantom crossing. Because early times the error bars are larger. So the phantom crossing seems to be below 2 sigma.
Yeah.
But at late times evolution seems to be near 3 sigma.
Near late times near 3 sigma?
She showed that if I'm not mistaken, the point where you have most sensitivity is around phantom crossing.
But that comes from the modeling fitting the whole time evolution.
That comes.
But also
No.
But also from data.
From data. The pivot scale is a property of a data set. So that's, it's a bit, such a tricky moment. It's also the time that dark energy started to take place.
Yeah, it's around 0.5. Right?
Yeah, it's the age of our planet. It's an uncomfortable time to be a cosmologist with all these coincidences. We have a model. I started a science called biocosmology that I have not yet had time to do much about, but it kind of comes when life started on the universe. There was this complexity, the biosphere, etc., that came out, and that's the same time of the appearance of domination by dark energy, of acceleration. I mean, it's very uncomfortable. Like, you'd like to have everything very well defined, but it's exciting times to be thinking. Just bear in mind try to keep together all of the things. If we isolate ourselves in our community, then we don't know how to talk to the theorists, to the phenomenology, to the data. So, excellent.
Okay, let's see more minutes up, so let's thank Marina again.
Thank you, guys.
Good talk.